The newborn universe was a sea of perfect, silent uniformity. It seems impossible that this smooth canvas could ever create the swirling majesty of galaxies or the intricate dance of solar systems. Yet everything we see, every star, every planet, and every one of us, was born from the faintest whisper of imperfection. This is the story of how the tiniest quantum ripples in the infant cosmos were stretched and amplified over billions of years into the grand structures of the modern universe. By the end, you will understand the unbroken chain of physics that connects the first fraction of a second after the Big Bang to the planet beneath your feet. How could microscopic randomness dictate the placement of galaxies? What invisible architecture guided the assembly of our own solar system? What does your existence reveal about the deepest history of everything? To grasp the origin of everything, we must rewind time to an almost incomprehensible moment. The universe was a mere fraction of a second old. It was not a void, but a seething, unimaginably hot and dense ocean of pure energy and the most fundamental particles. In this state, the very concepts of space and time as we know them were just beginning to form. Then something extraordinary happened. The fabric of spacetime itself began to expand at a rate far exceeding the speed of light, a brief but pivotal epoch cosmologists call inflation. This was not an expansion into anything, but rather the very stretching of reality itself. This explosive growth smoothed the universe out to an astonishing degree, ironing out any major wrinkles or irregularities. Yet it could not achieve perfect smoothness because at the tiniest scales the rules are different. Here, the bizarre laws of quantum mechanics reign. In this realm, empty space is never truly empty. It is a restless, frothing sea of potential, where pairs of virtual particles and their opposites constantly wink into and out of existence, borrowing energy from the universe for the briefest of moments. These are quantum fluctuations, the ultimate expression of randomness at the heart of reality. During that fleeting inflationary moment, as the universe stretched, it did not just stretch the smooth parts. It also stretched these infinitesimal quantum ripples. Imagine a tiny, random wrinkle on the surface of a balloon. Now, blow that balloon up to the size of a planet. That microscopic wrinkle becomes a vast, continent-sized ridge. Inflation did exactly that to these quantum whispers. It took fluctuations smaller than a single proton and inflated them to scales far larger than our entire observable universe today. In that act, the random quantum noise of the infant cosmos was frozen into the very geometry of space-time, etched into the fabric of the universe like a permanent, cosmic fingerprint. This is the primordial canvas. It appears perfectly smooth from a great distance, but up close, it holds the faintest of textures, an imprinted blueprint of random quantum events. This subtle, uneven landscape of density is the true starting point. From this apparent chaos, this delicate imperfection in an otherwise smooth expanse, the entire architectural plan for galaxies, stars, and planets was silently written. How could such microscopic randomness ever become a guiding map for the cosmos? These frozen ripples were not just random noise. They became the universe's first and most important architectural blueprint. The theory of cosmic inflation provides the crucial mechanism for this transformation, acting as the ultimate amplifier. During that unimaginably brief period of exponential expansion, the fabric of reality stretched so rapidly that it took those subatomic quantum jitters, fluctuations happening on a scale a billion times smaller than a single proton, and stretched them across the cosmos. They were no longer fleeting quantum events. They were locked in, frozen directly into the geometry of spacetime itself. Picture a single grain of sand on a perfectly smooth, deflated balloon. Now imagine that balloon inflating to the size of the entire Earth. That single grain of sand would become a mountain range spanning a continent. Inflation did precisely that to the quantum texture of the early universe. It did not just make the cosmos vast, it made it deliberately and predictably lumpy. This process created a spectrum of density variations, a cosmic code of hills and valleys in the distribution of matter and energy. Some regions were ever so slightly denser than others, packed with just a little more potential. These over-dense regions held a tiny gravitational advantage, a whisper of extra pull. They became the seeds, the gravitational blueprints for everything to come. This amplification from the quantum to the cosmic is the first, and perhaps most elegant, step in the journey from a smooth, uniform beginning to the intricate, structured universe we inhabit. Without this specific kind of lumpiness imprinted by inflation, the cosmos might have remained a forever smooth and featureless sea of particles, never coalescing into the grand structures that light up the dark. For nearly 400,000 years, the universe remained a thick, opaque fog. It was a searing plasma, so dense and energetic that light particles, photons, could not travel any meaningful distance without immediately colliding with a free electron. The cosmos was a glowing, trapped fireball. Then a pivotal threshold was crossed. As expansion continued, the temperature finally dropped enough for a fundamental transformation. Electrons slowed down and were captured by atomic nuclei, primarily hydrogen and helium, forming the first stable, neutral atoms. In an instant, the fog cleared. The universe, for the first time, became transparent. The light that had been trapped, bouncing furiously for all those millennia, was suddenly set free. That ancient flash of liberation is still traveling across the cosmos today. We see it as the cosmic microwave background radiation. It is the oldest light in existence, a baby picture of the universe when it was a mere 380,000 years old. This faint, uniform glow, detectable in every direction we look, is the afterglow of creation itself. But when cosmologists examine this snapshot with extraordinary precision, they find it is not perfectly smooth. Embedded within that uniform sea of microwaves are incredibly subtle patterns, tiny hot and cold spots where the temperature varies by just a few millionths of a degree. These are not random imperfections. They are the direct, fossilized imprints of those primordial density fluctuations from the inflationary epoch. The slightly denser regions, the gravitational seeds we discussed, appear as slightly cooler spots in the microwave background. Why cooler? Because light climbing out of a gravitational well, a region of higher density, loses a tiny bit of energy, shifting it to a longer, cooler wavelength. The slightly less dense regions appear as warmer spots. This map of temperature variations is a direct photograph of the gravitational landscape of the infant cosmos. It shows us precisely where matter was beginning to pool, the exact locations of the potential wells that would eventually draw in everything around them. Satellites like Planck have mapped this cosmic tapestry in breathtaking detail, allowing us to read the initial conditions of the universe as clearly as a fingerprint. This image confirms the predictions of inflation with stunning accuracy and gives us the starting blueprint. We can see, written in light from a time before stars or galaxies existed, the exact architectural plan for the entire cosmic web. The universe had its blueprint, but a blueprint is not a building. How did these faint gravitational whispers find the strength to pull together an entire cosmos? The universe now held a map of its own future, etched in light, but a map is not a territory. To build a cosmos from a blueprint requires a builder, and that builder is gravity. It is the weakest of the four fundamental forces, utterly dwarfed by the strength that holds an atomic nucleus together. Yet gravity has two profound advantages. It is always attractive, and it works over infinite distances. there is no cancelling it out. Once a region of space holds just a little more matter than its surroundings, its gravitational pull becomes ever so slightly stronger. This is the tipping point. Those subtle cold spots in the cosmic microwave background, those fossilized imprints of density, were not just temperature variations. They were gravitational wells, gentle dips in the fabric of spacetime where matter had already begun to pool. For millions of years, nothing seemed to happen on a human timescale. But across the cosmic deep, gravity was patient. It began its slow, relentless work. The slightly denser regions exerted their marginal extra tug, imperceptibly pulling on the thin soup of hydrogen and helium gas that filled the young universe. More importantly, they pulled on something else, something invisible and mysterious: dark matter. This enigmatic substance does not interact with light or electromagnetic forces at all. It feels only gravity. Because it does not experience pressure from radiation or collisions, dark matter was free to respond first to the gravitational whispers. It began to slide silently and smoothly into those pre-marked gravitational wells. Over eons, these accumulations of dark matter formed vast, diffuse spheres, immense halos that grew like invisible shadows in the dark. They became the hidden skeletons of the cosmos, immense gravitational scaffolds woven from a substance we cannot see. Without the outward pressure that normal matter experiences, these dark matter halos could condense and stabilize long before the visible universe could. They provided the crucial foundation. The hydrogen and helium gas, buffeted by the pressure of leftover radiation, needed these stable gravitational anchors. Once a dark matter halo reached a certain mass and density, its gravitational pull became a force that the ordinary gas could no longer resist. The invisible scaffolding was now strong enough to begin gathering the raw materials for light. This marks the profound transition in cosmic history. The smooth, nearly uniform sea of particles was gone. In its place were distinct gravitational seeds, each one a dark matter halo, each one a future galaxy waiting to be born. The universe had moved from a state of potential to a state of structure, but gas alone does not make a star. How did these dark cocoons ignite the first fires in the cosmic dark? Dark matter is the silent, invisible architect of our cosmos. While we cannot see it, touch it, or detect it with any telescope that observes light, its gravitational signature is written into the very structure of everything we can see. To grasp how galaxies assembled, we must follow the work of this unseen majority. In the composition of our universe, the ordinary matter that makes up stars, planets, and you and me, the stuff of protons and neutrons, accounts for less than 5% of the total cosmic budget. Dark matter, in contrast, makes up about 27%. Its defining characteristic is that it does not interact with the electromagnetic force. It feels gravity, but it is utterly blind to light. It does not scatter, absorb, or emit a single photon. This profound indifference was its superpower in the early universe. While the hot soup of ordinary particles, what scientists call baryonic matter, was being violently pushed around by intense radiation pressure, dark matter was free to move under the gentle, persistent tug of gravity alone. It did not get caught in the turbulent waves that buffeted normal matter. It simply began to slide silently and smoothly into the gravitational wells that had been imprinted during inflation. This gave it a colossal head start. Long before atoms could cool and settle, dark matter had already woven a vast, intricate scaffold across the expanding cosmos. Through powerful computer simulations like the famous Millennium Run, we can watch this process unfold. We see how those initial quantum seeds grow under gravity's relentless pull. Dark matter first forms a delicate cosmic web, a network of immense filaments that stretch across billions of light years, connecting at dense knots and intersections. This web is the underlying skeleton of the universe. it is not made of stars or gas, but of pure, invisible gravitational potential. These dark matter halos, especially at the intersections of filaments, became the deep gravitational wells necessary to finally trap the ordinary matter. The hydrogen and helium gas, once too energetic to be held, now flowed along these invisible channels, funneling into the waiting halos. Think of it like water following the subtle contours of a landscape it cannot see, gathering in valleys carved by a hidden hand. Without this pioneering work by dark matter, the ordinary matter might have remained a diffuse, formless haze forever, spread too thinly for gravity to ever gather it into stars. The invisible architect built the foundations, the immense gravitational basins, so that the visible universe could later pool within them and finally ignite. But gas in a gravitational well is still just gas. How did these dark cocoons spark the transformation from a cold, dark cloud to a blazing nuclear furnace? The stage was finally set for the visible universe to make its entrance. With the invisible scaffolding of dark matter firmly in place, the ordinary stuff of creation could at last begin its descent. For hundreds of millions of years, the primordial hydrogen and helium gas had been held aloft by the intense pressure of the lingering cosmic radiation, like dust particles suspended in a sunbeam. But as the universe expanded, that radiation thinned and faded, its push growing weaker and weaker. Gravity, the patient and persistent force, finally had its chance. The gas, now free to move, began to feel the relentless pull of those immense dark matter halos. This was not a sudden, catastrophic collapse, but a majestic and inevitable flow. Vast rivers of cold, pristine gas began streaming along the invisible highways of the dark matter web, following the gravitational contours of the cosmos toward the deepest wells. They converged at the intersections and knots of this cosmic skeleton, where the most massive dark matter halos resided. At these focal points, something spectacular began to take shape. Enormous, swirling reservoirs of gas accumulated, each one hundreds of thousands of light years across. These were the proto-galactic clouds, the raw, unformed material of future galaxies. Their fate, however, was not simply to be swallowed whole. The gas brought its own physics to the process. As it spiraled inward, it did not fall straight down. It possessed angular momentum, a legacy of the tiny twists and turns imparted during those earliest density fluctuations. This caused the infalling gas to flatten out, spinning faster and faster as it drew closer to the center, much like water swirling down a drain. This rotation prevented a simple, spherical collapse. Instead, these vast clouds began to pancake into immense, rotating disks. Meanwhile, the gas also generated internal pressure as atoms collided, creating a force that pushed back against gravity's crush. The delicate balance between gravitational pull, rotational spin, and internal pressure would sculpt the final form of each structure, determining whether it would become a majestic spiral galaxy like our Milky Way, a featureless elliptical blob, or something in between. Within these colossal, spinning nurseries, the conditions were becoming just right for a transformation far more brilliant. The gas was growing denser, and pockets within it were beginning to feel their own local gravitational pull, separate from the grand pull of the entire halo. In the deepest, coldest cores of these swirling clouds, the final ingredient for cosmic ignition was quietly gathering. Deep within those dark, swirling clouds, the first lights in the universe finally flickered on. They were not the familiar stars we see today. They were titans blazing with a ferocity we can scarcely comprehend. Astronomers call them population 3 stars, the first generation. They formed from gas that was pristine, untouched by any previous stellar cycle, composed of only hydrogen and helium, the raw elements forged in the Big Bang itself. To ignite nuclear fusion from such simple ingredients required immense gravitational pressure, and that demanded staggering size. These first stars were likely monsters, each 100s of times more massive than our own Sun. They did not form in great numbers or within grand spiral galaxies. Instead, they were born alone or in small clusters within the earliest and smallest dark matter halos. Picture a gravitational well holding the mass of 1,000,000 suns, a modest cradle by cosmic standards. Within that well, a single, colossal knot of gas would separate from the rest, collapsing under its own weight. As it shrank, temperatures at its core skyrocketed to millions of degrees. When the heat and pressure crossed a critical threshold, a new process ignited. Hydrogen nuclei began slamming together with enough force to overcome their natural repulsion, fusing into helium and releasing a torrent of energy in the process. The first star was born. Its light ended the cosmic dark ages, a profound dawn that began to flood the universe with photons for the second time in history. But this dawn was brief and violent. A star of such immense mass lives a life of extravagant haste. It burns through its nuclear fuel in only a few million years, a mere heartbeat in cosmic time. Its end is as transformative as its birth. When its core can no longer support itself against its own gravity, it collapses catastrophically and then rebounds in a titanic explosion, a supernova of unimaginable power. This is where the story of our own existence truly begins. In that final, furious blast, the alchemy of the cosmos advanced. The intense heat and pressure of the explosion forged the lighter elements into heavier ones. For the first time, atoms of carbon, oxygen, silicon, and iron were created and blasted out into the surrounding void. The shock waves from these first supernovae did more than just pollute. They acted like cosmic plows, churning the primordial gas, compressing it in some regions and dispersing it in others. They enriched the cosmic kitchen, sprinkling the ash of those first stars into the clouds that would form the next generation. This was the crucial step. The universe was no longer pristine. It now contained the heavy elements, the building blocks for rocky planets, for complex chemistry, and ultimately for life. The sacrificial death of those first, magnificent giants fertilized the cosmos for everything that would follow. Their legacy was not in lasting light, but in the scattered seeds of complexity they left behind. With this new, enriched material now drifting through the dark matter scaffolds, how would the next act of cosmic construction begin? The death of the first stars did not leave the universe empty. It left it seeded and ready for a new kind of growth. From that point forward, cosmic structure did not emerge fully formed. It built itself from the bottom up, piece by piece, in a grand hierarchical assembly. The process was not one of instant creation, but of relentless merging. Those early dark matter halos, having ignited their first stellar giants, became the smallest building blocks protogalaxies, each one a flickering island of a few million stars. They were not isolated. Gravity saw to that. Each tiny galaxy exerted a gentle tug on its neighbors. Over hundreds of millions of years, these tugs began to orchestrate a slow, gravitational dance. Pairs of these stellar islands would draw closer, their orbits decaying, until they finally spiraled into one another in a majestic, slow-motion collision. A galaxy merger is not a destructive crash like two cars meeting. It is a profound reorganization. The stars within are so far apart that they simply pass by one another, like two swarms of bees merging into a single, larger swarm. But the invisible dark matter halos surrounding them slam together and combine, creating a new, deeper gravitational well. The gas clouds within each galaxy, however, do collide. They crash together with tremendous force, sending shockwaves through the material. This often triggers a fireworks display of new star formation, a starburst, as the compressed gas rapidly collapses into a new generation of stars. With each merger, the central object grows in mass and gravitational influence. It becomes a more dominant anchor in the cosmic web, capable of pulling in more gas from the surrounding filaments and capturing smaller satellite galaxies that wander too close. This is how a dwarf galaxy, over billions of years, can grow into a majestic spiral or a vast elliptical galaxy. Our own Milky Way is a living museum of this bottom-up assembly. When astronomers map its outer halo, they find faint rivers and streams of stars' tidal tails. That are the dissolving remains of smaller galaxies it has consumed over its lifetime. We are, in a very real sense, the product of a cosmic cannibalism that has been ongoing since the universe was young. This hierarchical growth explains the rich variety of galaxies we see. A quiet, orderly merger might preserve a spinning disk to form a spiral like our own. A more violent, head-on collision could completely disrupt that spin, scrambling the stars into a smooth, football-shaped elliptical galaxy. Every galaxy's present form is a fossil record of its unique merger history, but galaxies are not the end of the story. They are merely the neighborhoods. Within these vast stellar cities, a far more local and intimate construction project was about to begin, one that would eventually lead to a stable, rocky world orbiting a steady, middle-aged star. The universe had built its stellar cities, but their final form was a matter of physics and spin. To understand why so many galaxies, including our own Milky Way, are not formless blobs but magnificent, flat pinwheels, we must look to a principle as familiar as a spinning ice skater. It is the conservation of angular momentum. In the early cosmos, those vast clouds of pristine gas falling into dark matter halos were not perfectly still. They possessed a tiny, inherited rotation, a gentle twist imparted by the gravitational tug of neighboring density fluctuations during the universe's infancy. This whisper of spin would become the defining feature of galactic architecture, as an immense cloud hundreds of thousands of light years across collapsed inward under its own gravity. A profound transformation occurred. Just as a figure skater pulls their arms in to spin dramatically faster, the collapsing cloud amplified its initial, slow rotation. The gas could contract easily along the axis of the spin, but perpendicular to that axis, the centrifugal force pushed back powerfully against gravity's pull. The result was inevitable. The cloud could not remain a sphere. It pancaked, flattening into a vast, thin, rotating disk. Within this enormous, spinning platter of gas and dust, the stage was set for the next act. The disk was not perfectly smooth. It rippled with turbulence and gravitational instabilities, regions where the gas grew slightly denser. These denser patches began to win their own local gravitational battles, pulling in more material from their surroundings. They fragmented the grand disk into billions of smaller, collapsing clumps. Each of these dense knots, a nursery in itself, continued to shrink and heat up until the fires of nuclear fusion ignited at its core. A star was born. This process, repeated across the entire disk over billions of years, populated the galaxy with its stellar inhabitants. But the story of the disk does not end there. The beautiful spiral arms we see in galaxies like ours are not solid, rotating structures. They are traffic jams of star formation, density waves that move through the galactic disk like ripples on a pond. As gas clouds enter these waves, they are compressed, triggering new bursts of star formation. The brightest, youngest, bluest stars light up these spiral arms, tracing out the pattern before they burn out quickly, leaving the older stars to drift away. This creates the illusion of permanent arms in a constantly changing flow. The final character of any galaxy, its ultimate size and the speed of its majestic spin, was largely locked in from the very beginning. It was dictated by the specific properties of its dark matter halo, the halo's total mass, its own inherent spin, and the rate at which it could draw in fresh gas. A massive, rapidly spinning halo would foster a grand spiral galaxy. A slower, more chaotic merger history might produce an elliptical galaxy without a disk. Our place in a spiral galaxy is not an accident. It is the direct legacy of a specific set of initial conditions, a particular amount of spin inherited from the quantum ripples of creation, carefully preserved and amplified over 13.8 billion years. But within this grand, spinning city of stars, a much quieter, more local story was beginning, one that would focus on a single, unremarkable clump in a nondescript spiral arm. The birth of stars is only half the cosmic story. Their death is the other, and it holds the key to why the universe looks the way it does today. When a massive star reaches the end of its brief, brilliant life, it does not fade quietly. It detonates. A supernova is one of the most energetic events in the cosmos, releasing in a single instant more light than our entire galaxy will emit over many months. This is not merely a spectacular light show. It is a fundamental regulating force, a cosmic pressure valve that shapes the destiny of galaxies. The shock wave from such an explosion travels outward at millions of miles per hour, a wall of energy that slams into the surrounding clouds of gas. It does two contradictory things at once. First, it violently heats the gas, making it so energetic that it cannot easily collapse to form new stars. Second, the force of the blast can actually sweep up vast quantities of this gas, driving it outward in powerful galactic winds. In the smallest, earliest galaxies, these winds could be so fierce they would blow the remaining star-forming material completely out into intergalactic space, effectively shutting down that galaxy's growth forever. This process is what astronomers call feedback. Think of it as the universe's own built-in thermostat for star formation. Without this violent, disruptive feedback, the story of galaxy evolution would be very short and very dull. A galaxy would simply convert all of its cool gas into stars in one frantic, brilliant burst, burning itself out in a cosmic flash. There would be no long-lived galaxies like our Milky Way, no steady trickle of star birth over billions of years. Feedback prevents this runaway collapse. It creates a self-regulating cycle. A burst of star formation creates many massive stars. Those stars live fast, die young, and explode. Their explosions heat and disperse the gas, slowing or stopping further star formation. Only when that agitated gas has time to cool, condense, and pool again can a new generation of stars ignite. This cycle of creation and destruction paces the life of a galaxy, but feedback does more than just regulate. It is the primary agent of cosmic recycling and enrichment. Within the heart of that supernova blast furnace, elements far heavier than helium are forged. Carbon, oxygen, silicon, iron, the very stuff of rocky planets and life itself, are cooked in those final moments and then blasted into the void. This enriched material, these metals as astronomers call them, mix with the pristine hydrogen and helium of the interstellar medium. The next generation of stars forms from this polluted, chemically rich gas. This changes everything. Gas enriched with metals can cool more efficiently, which actually makes it easier for smaller, denser clouds to form. This paves the way for the creation of smaller, longer-lived stars like our Sun, and crucially, for the formation of solid, rocky planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in the heart of a dying star and scattered across the galaxy by a supernova's feedback. The violent end of one stellar era thus becomes the fertile beginning of the next, setting the stage for a more complex, stable, and planet-friendly universe. Zoom out far enough, and the true architecture of the cosmos reveals itself. What we once saw as isolated islands of light are, in fact, connected points in a grand design. The universe is structured like a colossal, three-dimensional spiderweb, a tapestry woven from gravity itself. This is the cosmic web. It is the largest pattern in existence, stretching across billions of light years. At its heart are immense, dense knots where thousands of galaxies swarm together in massive clusters. Radiating from these knots are long, thread-like filaments, vast rivers of dark matter and gas along which galaxies are strung like pearls on a string. And between these structures lie the voids, unimaginably vast regions of near emptiness, cosmic deserts that can span hundreds of millions of light years and contain almost no galaxies at all. This sponge-like structure is not random. It is the direct, grown-up version of the baby picture we see in the cosmic microwave background. Those tiny temperature variations, those subtle hills and valleys in the early universe were the seeds. Under the relentless pull of gravity orchestrated by dark matter, the slightly denser regions drew in more and more matter over billions of years. The hills grew into mountain ranges, the galaxy clusters. The gentle ridges stretched into the long, connecting filaments, and the valleys expanded, emptying out to become the great voids. The pattern we see today in galaxy surveys, with its intricate network of walls and empty bubbles, matches the statistical fingerprint of those initial quantum ripples with breathtaking precision. It is a stunning confirmation that the same physics that governed the universe's first fraction of a second still sculpts its grandest structures today. We are not just looking at a map of where things are. We are looking at a living fossil of gravitational evolution, a single story told across the entire history of everything. At the heart of the cosmic web's grandest intersections, the universe builds its true metropolises. These are galaxy clusters, the largest structures in the cosmos held together by their own gravity. While a single galaxy is a vast city of stars, a cluster is an entire nation, a sprawling megalopolis containing hundreds or even thousands of individual galaxies, all orbiting a common center of gravity. Their sheer scale is difficult to fathom. They can span millions of light years, and their total mass is staggering, often a million billion times the mass of our own sun. But the galaxies themselves are merely the visible streetlights in this immense city. They account for only a small fraction of what is actually there. The true bulk of a cluster is composed of two invisible components. First, there is an absolutely immense reservoir of dark matter, whose gravitational grip forms the deep well that binds the entire structure together. Second, and perhaps more surprising, there is a vast, seething ocean of superheated gas. This is the intracluster medium. As galaxies and dark matter fell together over billions of years in the deepest gravitational wells, the ordinary gas that came with them was squeezed and compressed with such violence that it was heated to temperatures of tens of millions of degrees. This gas is so hot it does not shine in visible light, but instead glows fiercely in X-rays. For astronomers, this X-ray glow is a gift. It acts as a brilliant tracer, outlining the shape and size of the entire cluster and allowing us to literally weigh it. By measuring the temperature and distribution of this hot gas, scientists can calculate the total gravitational pull needed to contain it, revealing the cluster's true mass. This is how we discovered that the visible galaxies are just the tip of a monumental iceberg, with dark matter making up the overwhelming bulk of the cluster's substance. These colossal structures represent the final stage of the bottom-up assembly process. They are the modern-day descendants of the very densest peaks in that primordial fluctuation field, the regions that started with the greatest gravitational advantage 13.8 billion years ago. Their existence and their properties are a powerful test of our entire cosmic story. By counting clusters across cosmic time, cosmologists can perform a critical check on the universe's recipe. They can measure the total amount of matter, both dark and ordinary, and they can sense the opposing force that now shapes cosmic evolution on the largest scales: dark energy. This mysterious pressure, woven into the fabric of space itself, works against gravity's pull. It determines how quickly these great clusters could have assembled in the past and how their growth is slowing or even halting in the present epoch. In this way, galaxy clusters are not just endpoints. They are cosmic laboratories, holding within their immense grasp the clues to understanding the ultimate fate of the entire cosmic web. Our journey through cosmic structure now arrives at its most personal destination. After billions of years of expansion, gravitational collapse, and galactic assembly, the universe was finally ready to build solar systems. This transition from the galactic to the planetary scale is a story of incredible refinement, a filtering down of cosmic potential into a stable, local cradle. Within a majestic spiral galaxy like our own Milky Way, the space between the stars is not truly empty. It is filled with a diffuse mixture of gas and dust known as the interstellar medium. This material is the recycled remains of countless generations of stars, enriched with the heavy elements forged in their cores and supernova explosions. Most of this medium is thin and wispy, but scattered throughout the galactic disk are much colder, denser regions. These are the giant molecular clouds, cosmic nurseries so vast they can contain the mass of 1 million suns within a single, dark and frigid structure. They are the raw material reservoirs for new stellar generations. For such a cloud to begin forming stars, it needs a trigger, a passing spiral density wave, the gravitational wake of a nearby galaxy, or most powerfully, the shock wave from a supernova explosion can provide the necessary nudge. This external pressure squeezes a localized region within the cloud, pushing it over a critical threshold. The balance between internal gas pressure and the inward pull of gravity tips, and that pocket of the cloud begins to fall in on itself. This marks the beginning of a stellar nursery. As the cloud fragment collapses, it does not remain a single entity. The same forces of gravity, rotation, and turbulence that shaped galaxies now work on this much smaller scale. The large fragment breaks into smaller, denser knots, each one destined to become its own star system. In one such unremarkable knot, within a typical spiral arm of a standard spiral galaxy, a particular story began. This collapsing ball of gas and dust, spinning gently from the inherited motion of the galaxy itself, held within it the entire future of our solar system. It was an utterly ordinary beginning for what would become, to us, an extraordinary home. That collapsing fragment of cloud, destined to become our solar system, was not destined to form a single, solitary star. It held a far more intricate future within its spin. As gravity pulled the material inward, the same principle that shaped entire galaxies now worked on this local scale. The conservation of angular momentum, the slight rotation inherited from the galaxy's grand motion, became amplified. The cloud could not collapse into a simple sphere. Instead, it flattened like a cosmic pizza dough spun and stretched by gravity's invisible hands. The vast majority of the mass gathered at the very center, growing hotter and denser until nuclear fusion ignited, birthing our sun in its fiery infancy. But around this newborn star, the remaining material did not fall in. It swirled into a vast, flat, rotating disk. This is the solar nebula, a protoplanetary disk of gas and microscopic dust that stretched for billions of miles. This thin, luminous platter was the true construction site for planets. Its composition was a testament to cosmic history. The gas was primarily hydrogen and helium, the primordial elements. But mixed within it were countless trillions of microscopic solid particles, fine dust grains of silicates, carbon, and ices. These were not primitive. They were the direct, physical descendants of those ancient supernova explosions. The silicon and oxygen in the silicate grains, the carbon flecks, all were forged in the hearts of stars that lived and died long before our sun existed. We are literally seeing the recycled ash of stellar generations past, now gathered into this new construction zone. The structure of this disk was not uniform. It had a distinct temperature gradient, a slope of heat dictated by the young sun's fierce radiation. Close to the central furnace, temperatures were searing, far too hot for volatile compounds like water or methane to exist as solids. Only the most refractory materials, metals and rocky silicates with high melting points, could survive as solid grains in this inner inferno. Farther out, beyond a boundary astronomers call the frost line, temperatures dropped sufficiently for water, ammonia, and methane to freeze into solid icy grains. This simple division, this thermal map of the early disk, would become the single most important factor in determining the ultimate architecture of our solar system. It set the rules for what could be built and where, but dust, even dust enriched with starlight's legacy, is just dust. How could these microscopic specks possibly grow into the majestic, complex worlds we know today? From microscopic dust, a new world must begin. This is the quiet, almost invisible phase where the universe transitions from scattered ingredients to solid architecture. Within the luminous protoplanetary disk swirling around our infant sun, countless trillions of dust grains drift in a thin haze. Each one is a survivor, a fleck of stardust forged in distant stellar furnaces. They are the fundamental bricks, but bricks do not spontaneously assemble a cathedral. They need a force to bring them together, and in the near-perfect vacuum of space, that initial force is surprisingly gentle. It is not gravity, not yet. It is a weak electrostatic attraction, a subtle stickiness at the atomic level. When two of these microscopic particles drift close enough, they cling together, much like a stray dust bunny might cling to a wool sweater. This simple, persistent process is called coagulation. It is the universe's most humble act of construction. Over thousands of years, these random encounters build up. A single grain becomes a tiny cluster. That cluster bumps into another, merging into a larger, fluffy aggregate. Think of it like building a snowball in zero gravity, one fragile snowflake at a time. These growing clumps, from microscopic to millimeter, then centimeter, then meter in size, are no longer mere dust. They are becoming something new, yet this delicate growth faces a constant threat. The disk is not still. It is a turbulent, spinning environment. Gas swirls around at different speeds, creating drag. A meter-sized chunk of rubble moving through this gas experiences a kind of cosmic headwind. This friction saps its orbital energy, causing it to drift slowly but surely inward toward the sun. Left unchecked, this drift would doom all this material to a fiery end, vaporizing long before it could become a planet. But physics provides a saving grace. As these objects grow, they also begin to settle. The drag from the gas acts more strongly on smaller, fluffier particles. The larger, more compact aggregates feel it less. Gradually, over time, the disk begins to separate. The finest dust remains suspended in the upper layers, while the growing pebbles and boulders sink toward the central plane of the disk, a region called the midplane. Here, in this denser, calmer highway, the building blocks find their community. The local density of solid material skyrockets. What was once a diffuse haze becomes a crowded river of rubble, all orbiting in the same direction. This is the tipping point. When the concentration of material in the midplane grows high enough, the game changes entirely. The weak stickiness that built the first snowballs is no longer the dominant force. Now gravity takes the lead. A kilometer-sized chunk of rock and ice possesses enough mass to exert its own tiny but meaningful gravitational pull. It can attract nearby smaller objects, drawing them in for collisions that are no longer gentle mergers but impactful events. These kilometer-sized bodies are the true turning point. They are called planetesimals, the fundamental building blocks of planets. This stage is one of incredible chaos and violence, a dusty demolition derby on a cosmic scale. Planetesimals of all sizes zip through the crowded midplane, their orbits crossing. Collisions are frequent. Some are accretive, where a smaller body splats onto a larger one, adding to its mass. Others are destructive, where two similar-sized bodies smash each other into a cloud of fragments, only for that debris to later recoalesce. It is a relentless, churning process of construction and destruction, where only the largest, most resilient, or luckiest objects survive and grow. The efficiency of this entire grand experiment, whether it produces a handful of large worlds or just a scattered belt of rubble, hinges on one critical factor set billions of years earlier: the local density of solids in that region of the disk. Near the frost line, where ice joined rock to double the available building material, this density was high. The planetesimal factory there worked overtime. In the hotter inner disk, where only rocky grains could survive, the density was lower, the process more delicate. From this chaotic, collision-dominated arena, the true architects of our solar system were beginning to emerge, their fates written in the initial distribution of dust and the relentless, simplifying logic of gravity. Gravity's gentle tug becomes a commanding pull. Once a planetesimal grows to roughly a kilometer in size, its influence expands dramatically. It is no longer just a passive target in the cosmic shooting gallery. It now possesses enough mass to exert its own meaningful gravitational field, a sphere of influence that extends into the space around it. This changes the entire game of accretion. Smaller objects passing nearby are no longer just on random trajectories. They are gently deflected by this new gravity well, their paths bending ever so slightly toward the growing body. This dramatically increases the collision cross-section, the effective target size of the large planetesimal. It is no longer just hitting what it directly runs into. It is now pulling material in from a wider volume of space. This creates a powerful feedback loop. The more mass it gains, the stronger its gravitational reach becomes. The stronger its reach, the more efficiently it can sweep up material from its surroundings. This is the phase of runaway growth, where the largest bodies in any given orbital zone begin to outpace all their smaller neighbors at an accelerating rate. They snowball in mass, becoming the gravitational bullies of their local neighborhood. Within a few 100,000 years, this process transforms the chaotic rubble field. From the countless anonymous planetesimals, a handful of clear leaders emerge. These burgeoning objects are called planetary embryos or protoplanets. They are substantial worlds in their own right, ranging from the size of our moon to that of Mars. Each one is a molten sphere of rock and metal, heated by the relentless energy of impacts and the decay of radioactive elements forged in that ancient supernova. Their emergence brings a new kind of order, but also a new kind of conflict. Each dominant embryo begins to clear its orbital path. Through a combination of direct collisions and gravitational scattering, it either consumes or flings away the remaining smaller debris in its vicinity. Think of it as a cosmic street sweeper tidying its lane in the great orbital highway. The once smooth and dusty protoplanetary disk is now visibly transformed. It is no longer a uniform haze. Instead, it contains a distinct architecture, a series of spaced-out, massive embryos, each holding court in its own feeding zone, a swath of disk from which it draws material. They are not yet the planets we know, but they are their undeniable precursors, locked in stable orbits around the young sun. For a time, there is a tense equilibrium, a balance of power governed by their spacing and the sun's gravity. But this peaceful coexistence is fragile. The disk is still dynamic, and the gravitational influence of these growing embryos does not respect neat boundaries. Their spheres of influence begin to edge closer, their subtle tugs on one another slowly, inexorably, destabilizing the delicate balance. The stage is now set for the final, most dramatic act of planetary construction, a period of colossal impacts and chaotic rearrangements that will forge the solar system we recognize today. The peaceful era of planetary embryos could not last. Their growing gravitational influence began to weave a web of subtle, chaotic interactions. The delicate balance of power between these massive protoplanets, each holding its own orbital lane, was inherently unstable. Their mutual tugs gradually perturbed one another's paths, shifting orbits from neat circles into intersecting ellipses. This set the stage for the final, most violent chapter of planetary construction, a period of giant impacts that would forge the final forms of the terrestrial worlds. The most famous of these cataclysmic events in our own cosmic backyard involved a world we will never see. A Mars-sized protoplanet, which scientists have named Theia, is believed to have crossed Earth's path. The resulting collision was not a glancing blow, but a head-on, world-shattering merger. The energy released was beyond comprehension, enough to vaporize rock and metal and melt the entire early Earth into a global, seething magma ocean. From this apocalyptic fire, our moon was born. The colossal impact ejected a vast torus of vaporized debris from both bodies into orbit around Earth. This incandescent ring of rock and metal quickly coalesced, cooling and solidifying into the familiar companion that has graced our skies ever since. This single event did more than give us a moon. It fundamentally reset Earth, stripping away any primordial atmosphere and superheating the entire planet, setting the stage for everything that followed. The violence of such impacts was not unique to Earth. Every terrestrial planet bears the scars of this final bombardment. Mercury's oddly large metallic core may be the remnant of a colossal collision that stripped away much of its mantle. The slow, backward rotation of Venus might be a legacy of a titanic impact that flipped the planet upside down. The Martian hemisphere dichotomy, the striking difference between its smooth northern plains and cratered southern highlands, could also be the scar from a planet-altering strike. These were the defining moments that sculpted the final personalities of the inner solar system. Yet from this chaos came a crucial order. The immense energy of these giant impacts, combined with heat from radioactive decay, kept the young planets molten for millions of years. In this liquid state, gravity performed a final, critical act of organization: planetary differentiation. Dense, heavy elements, primarily iron and nickel, sank through the global magma ocean like stones through water, pooling at the center to form a dense metallic core. Lighter silicate minerals, the rocky material, rose to the surface, cooling to form a mantle and eventually a thin, solid crust. This process created a layered internal structure, a planetary onion with distinct shells. This differentiation is not just a geological detail. It is the single most important factor in creating a living, dynamic world. A metallic core, churning due to residual heat and the planet's rotation, can generate a global magnetic field. This invisible shield deflects the solar wind, protecting a planet's atmosphere from being stripped away into space and shielding the surface from harmful radiation. Meanwhile, the heat engine of a cooling interior drives geological activity, volcanism, mountain building, and the slow conveyor belt of plate tectonics. Without that violent, molten rebirth and the ensuing internal sorting, Earth would be a geologically dead, airless rock, its surface static and exposed. The final bombardments were a brutal but necessary crucible, forging not just planets but the very conditions that could one day nurture complexity. This invisible thermal boundary, the frost line, is the single most important zoning law in the cosmos. It is not a physical wall, but a region of shifting temperature within that spinning protoplanetary disk. Close to the young sun's fierce heat, only the most stubborn materials could survive as solids. Metals like iron and rocky silicates remained as microscopic grains, the building blocks of future terrestrial worlds. But venture farther out beyond this thermal frontier, and the environment changes dramatically. Temperatures drop enough for a magical transformation. Volatile compounds that would forever be gases in the inner system water, ammonia, methane freeze into solid icy grains. This simple fact of phase change of gas turning to ice has a staggering consequence. It effectively doubles or even triples the amount of solid building material available in the outer disk. Imagine two construction sites. One has only bricks. The other has bricks and an unlimited supply of lightweight, sticky snow. The builders at the second site have a profound advantage. they can assemble structures of immense size, and they can do it quickly. This is exactly what happened in our early solar system. Inside the frost line, the accretion of planetesimals was a meticulous, slower process. The available rocky material was limited, and the growing embryos had to compete fiercely for every last gram. They built compact, dense worlds of rock and metal: Mercury, Venus, Earth, and Mars. Their final sizes and compositions were dictated by the modest pantry of solids in their hot neighborhood. But beyond the frost line, the construction project exploded in scale and ambition. With ice grains now mingling with the silicate dust, the density of solid material in the disk skyrocketed. Planetesimals there grew at a breakneck pace during the phase of runaway growth. They were not just balls of rock. They were dirty snowballs, cosmic conglomerations of ice and stone, and their increased mass allowed them to dominate their orbits even more efficiently. The largest of these snowball cores grew to an astonishing size, roughly 10 times the mass of our entire Earth, and at that critical threshold, everything changed again. A core of that immensity possesses a gravitational pull so powerful that it can begin to do something entirely new. It can start capturing the lightest and most abundant elements in the disk, the primordial hydrogen and helium gas that had been swirling past all this time. This is the birth of a gas giant. The process is called runaway gas accretion. Once it begins, it is a self-fueling frenzy. The growing envelope of gas adds more mass, which increases the gravitational pull, which captures even more gas at a faster rate. In what is, cosmically speaking, the blink of an eye, a world transforms. A massive icy rocky core becomes the seed for a planetary atmosphere of incomprehensible scale, swallowing enough hydrogen and helium to become 1,000 times more massive than the Earth. This is how Jupiter and Saturn were born. Their majestic, swirling atmospheres are not their true identity. They are the trophies captured by a colossal, hidden core that won the gravitational lottery beyond the frost line. This single thermal boundary, therefore, wrote the master plan for our entire solar system's architecture. It dictated a clear division, an inner zone of small, rocky planets and an outer kingdom of gas giants, with a belt of leftover icy rubble, the asteroids and comets marking the frontier between them. Every planetary system we discover among the stars tells its own version of this story, its own frost line etched by the heat of its parent star, forever determining what kinds of worlds can form and where they can call home. The solar system's architecture was not set in stone from the moment the planets formed. In fact, the story of where a planet ends up is often as dynamic as the story of its birth. For millions of years after the giant planets coalesced, the young solar system was not the near vacuum we know today. It was still filled with the remnants of the protoplanetary disk, a diffuse but substantial sea of gas and dust. Within this environment, a planet is not a solitary traveler. It is an object moving through a fluid, and that interaction can rewrite its destiny. This process is called orbital migration, and it represents a solar system's turbulent adolescence. A massive protoplanet, like a young Jupiter, does not simply orbit in silence. Its immense gravity tugs on the surrounding gas disk, creating spiral density waves, ripples in the fabric of the disk itself, much like the wake of a boat moving through water. These waves are not one-sided. They exert a gravitational torque back on the planet, depending on the intricate balance of forces inside and outside the planet's orbit. This exchange can either sap its orbital energy, causing it to spiral slowly inward toward the star, or add energy, pushing it outward. It is a delicate gravitational dance where the planet and the disk that birthed it are locked in a final, fateful conversation. This explains one of the most puzzling discoveries of the exoplanet era: hot Jupiters. These are gas giant planets similar to Jupiter in mass, but found orbiting blisteringly close to their host stars, completing an orbit in mere days. They could not have formed there. The searing heat so close to a star would have prevented the icy core accretion necessary to build a gas giant. The leading explanation is that these worlds formed much farther out, in the cool reaches beyond their system's frost line, and then migrated inward over millions of years, driven by interactions with their primordial gas disk. They are cosmic drifters, worlds that embarked on a grand journey to end up in a place utterly unlike their birthplace. Our own solar system bears the subtle scars of this dynamic past. While we have no hot Jupiter, astronomers believe a grand reshuffling likely occurred here as well, a dramatic event captured by what is known as the Nice model. In this scenario, after the gas disk had dissipated, the giant planets Jupiter, Saturn, Uranus, and Neptune initially orbited in a much more compact, closer-knit configuration. Their orbits were nestled within a vast, distant belt of icy planetesimals, the leftover debris from the outer solar system's construction. Gravitational nudges between the giants and this sea of icy bodies slowly destabilized the entire arrangement. This triggered a period of orbital instability, a gravitational pinball game that lasted perhaps 100 million years. Jupiter likely moved slightly inward, while Saturn, Uranus, and Neptune were scattered outward. In the process, Neptune may have swapped places with Uranus, and a torrent of icy debris was hurled inward, raining down upon the inner solar system in a cataclysmic event called the Late Heavy Bombardment. The evidence for this is written in the cratered faces of the Moon and the outer solar system's current, seemingly arranged orbits. This dynamic phase reveals a crucial truth. A solar system is not a clockwork mechanism assembled and left to tick. It is a living, breathing entity in its youth, capable of dramatic rearrangement. The peaceful order we see today is the calm after a long and formative storm. The young star's fiery temper finally subsides. After a few million years of furious fusion, its internal structure stabilizes, but its surface erupts with a new kind of violence. This is the T-Tauri phase, a stellar adolescence marked by tantrums of cosmic proportion. The star now unleashes powerful stellar winds, a supersonic gale of charged particles flowing outward in all directions. Coupled with an intense barrage of ultraviolet and X-ray radiation, this outpouring creates an invisible but immense pressure, pushing against everything in its vicinity. The once dense protoplanetary disk, the very cradle of planetary formation, now faces an existential threat. This stellar hurricane acts like a cosmic broom. It sweeps through the system, relentlessly pushing against the thin veil of hydrogen and helium, gas that still lingers from the disk's earliest days. For the gas giant planets, this moment is a hard deadline. Their runaway accretion of atmosphere, the process of swallowing surrounding gas, depends on that gas being present. Once the T-Tauri winds blow it all away into interstellar space, the buffet closes forever. Jupiter and Saturn had already grown to gargantuan size, their feasting largely complete. But any smaller, slower-forming gas giants, or the icy cores still trying to capture an atmosphere, are abruptly cut off. Their growth halts in an instant, frozen in an unfinished state. This phase is equally transformative and brutal for the inner rocky worlds. If a planet like Earth or Venus had not yet cooled sufficiently to form a solid, massive core and a protective magnetic field, this stellar onslaught could strip away its entire primordial atmosphere, blasting it into the void. A world might be left as a barren, naked rock before it ever had a chance to nurture oceans or air. The T-Tauri phase is the universe's way of enforcing a final construction deadline. It clears the workshop. What remains after this great clearing is a fundamentally different solar system. The thick, glowing nebula is gone. In its place is a far more transparent environment, a thin debris disk of leftovers. This is the population of planetesimals that never grew into planets, the asteroids and comets that avoided being consumed or ejected. They are the construction rubble, the spare parts of planetary assembly. With the gas removed, the dynamic friction that caused orbital migration ceases. The planets, now isolated in largely empty space, settle into the nearly stable orbits they will occupy for billions of years. The primary era of planet building is over. The solar system has taken its modern shape, yet this new clarity brings its own form of chaos. With the stabilizing gas gone, the gravitational interactions between the giant planets and this vast sea of leftover debris become more direct, more chaotic. This sets the stage for the system's final act of violence, a long period where the remaining rubble is hurled inward, pummeling the young worlds in a celestial bombardment that will both scar and seed them. The calm after the solar system's formation was an illusion. For hundreds of millions of years, a hidden reservoir of chaos lingered in the cold, dark reaches beyond Neptune. Then the gravitational peace was shattered. Evidence is written across the face of our moon, a silent witness to a time of cosmic violence called the Late Heavy Bombardment. The lunar highlands, those ancient, light-colored terrains, are saturated with craters. But when scientists dated the rocks brought back by the Apollo missions, they found something startling. Many of the immense impact basins, like the Sea of Rains and the Sea of Serenity, formed not in the first 100 million years, but in a relatively narrow window much later, between 500 million and 1 billion years after the solar system began. This points to a dramatic spike in impacts, a celestial storm that rained down across the inner solar system long after the planets had supposedly settled into place. This was no random accident. It was the delayed consequence of the giant planets' restless dance. As Jupiter, Saturn, Uranus, and Neptune gravitationally jostled in their new, unstable orbits, their immense gravity acted like a cosmic slingshot. The outer solar system was still filled with a vast swarm of icy planetesimals, the leftover building blocks that never coalesced into another world. The shifting giants perturbed this sea of frozen debris, hurling countless chunks of rock and ice onto new, elliptical paths that crossed the orbits of the inner planets. For tens of millions of years, the inner solar system became a shooting gallery. Asteroids and comets, some hundreds of miles across, screamed inward on collision courses. The scarred surfaces of Mercury, Mars, and our moon bear permanent testimony to this era of cosmic crossfire. Earth would have received its share of these cataclysmic blows, each impact releasing more energy than all the world's nuclear arsenals combined, vaporizing rock and boiling any early oceans into steam. It was an epoch of seemingly pure destruction, yet from this chaos a profound paradox emerged. These icy comets and water-rich asteroids from the outer solar system were not just projectiles. They were also delivery vehicles. While the impacts themselves were sterilizing events, the material they carried may have been the very gift of life. The inner planets, including Earth, formed inside the frost line, too hot for water ice to condense. They were born dry and rocky. The comets and asteroids that pummeled them, however, were rich in volatile compounds, water, ammonia, and complex organic molecules like amino acids. With each impact, some of this precious cargo could have survived, either buried within the impacting body or delivered in the aftermath by a steady rain of smaller debris. Over millions of years, this bombardment may have filled Earth's basins with water, creating the first true oceans, and sprinkled the planet's surface with the essential chemical precursors for biology. The very event that rendered the surface hellish also, in time, provided the ingredients to make it a cradle. The late heavy bombardment stands as a pivotal reminder that in the cosmos, creation and destruction are often two sides of the same coin, and our existence may hinge on a period of ancient, violent grace. Our place in the cosmos is not a random accident, but the end product of an almost unimaginably precise sequence. From the faintest quantum whisper to a world teeming with life, every single link in that chain had to be exactly right. The initial spectrum of those fluctuations, their specific pattern of hills and valleys, did more than just seed galaxies. It dictated the eventual distribution of all matter, setting the gravitational stage upon which every future event would play out. Had those quantum ripples been slightly louder or softer, the cosmic web would have woven a different tapestry. Perhaps galaxy clusters would have been too sparse or too densely packed, altering the very environments where stars are born. The nature of dark matter itself was another non-negotiable prerequisite. Its unique properties, its indifference to light, and its responsiveness only to gravity orchestrated the timing of cosmic dawn. If dark matter interacted even weakly with radiation, those first gravitational scaffolds would have formed too late or not at all, leaving the ordinary matter forever adrift in a formless haze. The universe required this invisible, patient architect to build the foundations on schedule. Then came the alchemy of the stars. The life cycles of the earliest stellar generations were not just about making light. They were cosmic kitchens, and their recipes were critical. The rate of supernova explosions, the specific mix of heavy elements they forged, carbon, oxygen, iron, and all the others, this determined the chemical enrichment of our entire galactic neighborhood. Too few supernova, and the interstellar medium remains barren, devoid of the elements needed for rocky planets. Too many, and the resulting radiation and turbulence could sterilize entire regions of the galaxy, preventing the quiet, stable periods necessary for planetary systems to coalesce. Zooming into our own spiral arm, the story becomes even more contingent. Our solar system began as one anonymous fragment within a giant molecular cloud. That particular cloud had to be triggered to collapse at just the right time, from a nearby supernova shockwave or a spiral density wave. The fragment that became our system possessed a specific amount of spin, inherited from the galaxy's grand rotation, which dictated the size and structure of the protoplanetary disk. Within that disk, the location of the frost line determined where rocky and gaseous worlds would form. Earth's assembly was itself a violent ballet of chance. The giant impact that gave us our moon was a catastrophic event with a staggeringly low probability, yet it was essential for stabilizing Earth's tilt and creating the conditions for a stable climate over billions of years. All of these steps, each one dependent on the precise outcome of the last, funneled down to a single, remarkable result: a rocky planet of the right size and composition, orbiting steadily within its star's habitable zone where water can exist as a liquid. A world protected by a magnetic field, fueled by geological heat, and seeded with the legacy of ancient starlight. We are the beneficiaries of a cosmic lottery of almost impossible odds, a testament to a universe whose fundamental laws allow simplicity to mature over deep time into profound and beautiful complexity. The beauty of this cosmic story lies not in its elegance alone, but in its testability. We are not simply weaving a philosophical tale. We are reconstructing a history supported by a vast and converging web of hard evidence, where predictions made decades ago are now confirmed with breathtaking precision. The first and perhaps most profound pillar is the cosmic microwave background. Satellites like WMAP and Planck have mapped its subtle temperature variations, those millionth of a degree hot and cold spots, with extraordinary detail. The statistical pattern of these anisotropies, their size and distribution across the sky, is not random. It matches the specific predictions made by models of cosmic inflation with almost uncanny accuracy. It is a direct snapshot of the universe at 380,000 years old, and it shows us the exact gravitational seeds that our theories said should be there. This ancient light is the first crucial link in the chain, confirming the initial conditions from which everything grew. Moving forward in time, we turn to the architecture of the modern universe. Massive astronomical projects like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument have undertaken a monumental task, meticulously mapping the positions and distances of millions of galaxies. The three-dimensional picture they reveal is the cosmic web in all its glory, a vast sponge-like structure of clusters, filaments, and voids. This observed distribution is not what you would get from a random scattering of points. Its statistical fingerprint, the way galaxies cluster on different scales, aligns perfectly with supercomputer simulations that start with those CMB seeds and model the gravitational growth driven primarily by dark matter. We can literally watch a simulation evolve from a smooth, rippled beginning into a web that looks identical to the one we observe today. This is a powerful, independent confirmation that our understanding of structure formation is correct. Finally, we zoom in to witness the very process of planetary birth in action. The Atacama Large Millimeter Array, ALMA, is a radio telescope of stunning power, capable of peering into the dusty disks surrounding young stars. What it has found is nothing short of revelatory. In system after system, these protoplanetary disks are not smooth, featureless platters. They show distinct gaps, bright rings, and spiral arms. These features are the predicted signposts of planet formation, the gravitational signatures of young, unseen worlds carving their paths through the dust and gas as they gather material. We are seeing the frost line in action, watching as different materials freeze out at different distances from the star, creating the conditions for diverse worlds to form. ALMA provides a real-time glimpse of a process that, in our own system, concluded over 4 billion years ago. Each of these observational pillars, the CMB, the galaxy surveys, the protoplanetary disks, connects a different epoch in our cosmic story. They are not isolated facts. They weave together into a single, coherent narrative that stretches from the first quantum tremors to the swirling cradles of new solar systems. The theory makes a prediction, and the universe, through our telescopes, answers back with a resounding confirmation. This is the strength of the scientific epic, a story written not in words, but in light, gravity, and the relentless pursuit of evidence. Yet for all the breathtaking connections we have traced, the story is far from finished. Our cosmic narrative, so elegantly woven from the quantum to the galactic, still contains profound and humbling gaps. We have mapped the influence of dark matter with exquisite precision, but we still do not know what it is. We measure the accelerating push of dark energy, but we cannot explain its origin or its ultimate implications. These two invisible components govern the fate of the cosmos, yet they remain complete mysteries, the dominant forces in a universe we barely understand. The engine that started it all, cosmic inflation, is a powerful theoretical framework that fits the data beautifully, but we still lack direct proof of the physical mechanism that triggered it. Was it a field, a phase transition, something entirely unforeseen? Answering this means peering into the first sliver of a second, a realm where our current physics breaks down. Our perspective is also inherently limited. We have built our cosmic story from a single data point, our own solar system, in one galaxy among trillions. New telescopes are revealing an astonishing menagerie of exoplanets, worlds of every conceivable size and orbit, from diamond planets to water worlds to hot Jupiters. This dazzling diversity forces us to ask deeper questions. How common is a system like ours with rocky planets nestled in a temperate zone? What combination of initial conditions, disk properties, and chaotic dynamics leads to such variety? Is our peaceful, stable arrangement a cosmic rarity or a commonplace outcome? And looking even broader, are the specific initial conditions that spawned our universe, the exact strength of those quantum ripples, the precise amounts of matter and energy unique? Or are they merely one possible outcome in a vast, perhaps infinite, multiverse, where other universes with different laws flicker into existence beyond our perception. These are not philosophical musings. They are the driving questions for a new generation of observatories that will redefine our vision. The James Webb Space Telescope is acting as a time machine, peering back to capture the light of the very first galaxies, watching them assemble in real cosmic time. The Vera C. Rubin Observatory will soon begin a decade-long movie of the night sky, mapping billions of galaxies and tracking subtle changes that will shed new light on dark matter and dark energy. And on the horizon, next-generation gravitational wave detectors promise to listen for the echoes of cosmic inflation itself, a faint hum from the birth of spacetime. Each new instrument is a key designed to unlock one of these enduring mysteries. The story of how our universe grew from a whisper to a web is a triumph of human curiosity, but it is also an unfinished manuscript. The most thrilling chapters may still be waiting, written in the dark, in the distant past, and in the physics we have yet to discover. This fine-tuning of cosmic history is not merely a curious fact. It is a profound puzzle that echoes from physics into philosophy. The universe we observe possesses a very specific set of starting parameters. If the initial quantum fluctuations had been even slightly stronger, matter would have clumped together with ferocious intensity. Over-dense regions would have collapsed directly into black holes long before stars could ever form, creating a dark and sterile cosmos. If those fluctuations had been slightly weaker, the gravitational seeds would have been too feeble. Matter would have remained a diffuse, forever spreading haze, never gathering into galaxies or planets. Our existence, therefore, hinges on a razor-thin balance within those first moments. This observation leads to a simple but powerful idea known as the anthropic principle. In its most basic or weak form, it is almost a statement of the obvious. We can only find ourselves in a universe capable of producing us. We observe the particular cosmic conditions that allow for galaxies, stars, planets, and chemistry because, well, we are here to observe them. If the conditions were different, there would be no observers to ponder the question. This is not an explanation for why the universe is this way. It is a logical constraint on what we can possibly see. Yet this simple framing opens a door to some of the most profound questions in all of science. Why does the universe seem so exquisitely calibrated for complexity? One compelling answer emerging from theoretical physics is the concept of a multiverse. In this view, our universe with its specific rules and constants might be just one bubble in a vast, perhaps infinite, cosmic foam. Each bubble universe could have different physical laws, different strengths of forces, and different types of primordial fluctuations. In most of these universes, the numbers would not line up right. They would be stillborn or chaotic, incapable of generating structure or life, but in a rare few, by pure statistical chance, the dials would be set just so. We inevitably find ourselves in one of those rare, life-permitting bubbles, simply because we could not exist anywhere else. The multiverse idea transforms fine-tuning from a mystery into a selection effect. Another possibility is that there is no multiverse at all. Perhaps there exists a single, elegant, and deeper theory of everything that uniquely predicts the constants we see. In this view, the universe is not tuned by chance, but by necessity. The laws themselves may demand a cosmos that can eventually become self-aware. This is a more contentious and philosophical stance, pointing toward a cosmos with a built-in direction or potential. Both paths, the multiverse and a deeper principle, push at the very boundaries of our understanding. They ask us to consider whether the story that began with a quantum whisper was a random roll of cosmic dice, or the opening chapter of a narrative written into the fabric of reality itself. These grand questions may one day be answered not just by telescopes but by machines. To truly understand the chaotic, non-linear dance of cosmic evolution, we must build our own universes. Inside the world's most powerful supercomputers, cosmologists do exactly that. They begin with a simple, virtual box of space, filled with millions or even billions of simulated particles representing dark matter and primordial gas. Each particle is given a tiny push based on the precise map of fluctuations we see in the cosmic microwave background. Then, with a press of a button, they set the simulation in motion. The laws of physics coded into every line of the program take over. Gravity begins its relentless work, pulling the dark matter particles into the familiar cosmic web of filaments and halos. The gas follows, cooling and flowing into those dark scaffolds. Regions collapse, temperatures soar, and when conditions are just right, the simulation triggers the birth of a star, releasing energy that then pushes back on the surrounding gas. This cycle of creation and feedback plays out over billions of virtual years, compressed into mere months of computation. The results are nothing short of breathtaking. Projects like Illustris TNG and Eagle produce virtual universes that are eerily familiar. When you look at a snapshot from one of these simulations, you do not see abstract data points. You see a rich tapestry of structure. Majestic spiral galaxies rotate within massive clusters. Delicate filaments of gas connect nodes in a vast, three-dimensional web. These digital universes evolve with a realism that matches our deepest sky surveys, but their true power is not in their beauty. It is in their role as a cosmic laboratory. Inside a simulation, scientists can run experiments impossible in the real world. They can switch off supernova feedback with a single command and watch as galaxies burn out in a frantic, short-lived burst. They can remove dark matter entirely and see a universe that never forms any structure at all. They can rewind a specific galaxy's violent merger history to understand why it looks the way it does today. These virtual realms allow us to isolate single variables in the immensely complex recipe of cosmic growth, testing our theories with a precision pure mathematics could never provide. They bridge the profound gap between the elegant simplicity of our initial equations and the gloriously messy, interconnected reality we observe. Every time a simulation successfully predicts a new feature later found by our telescopes, it is a powerful vote of confidence that our story, from quantum seed to galactic city, is on the right track. This realization ties the grand cosmic story directly to the very substance of our being. Every atom in your body that is heavier than the simplest elements, hydrogen and helium, carries a profound legacy. It was forged in a crucible far more extreme than any on Earth, deep within the core of a star, under crushing gravitational pressure and temperatures reaching millions of degrees. A process called nucleosynthesis takes place. Here, the nuclei of lighter atoms are slammed together with such immense force that they fuse, creating newer, heavier elements. In a star like our Sun, this primarily fuses hydrogen into helium. But in more massive stars, the furnace burns hotter and the alchemy advances. Helium fuses into carbon, carbon into oxygen, and so on up the periodic table, creating neon, magnesium, silicon, and eventually iron at the very center. This is where the story inside the star ends, as fusing iron consumes energy instead of releasing it. The star's fate is now sealed. When its core can no longer resist gravity's pull, it collapses and rebounds in a cataclysmic supernova explosion. In that final, furious blast of energy, even heavier elements are created: gold, silver, uranium, and all the newly forged material from carbon to iron is violently ejected into the surrounding space. This stellar debris, this enriched ash, mixes with the interstellar gas. Over billions of years and countless generations of stars living and dying, the chemical composition of the galaxy evolves. The thin haze between the stars becomes gradually sprinkled with these heavier atoms, the building blocks of complexity. This process of chemical enrichment is the indispensable link between the birth of galaxies and the chemistry of life. Without those earlier stellar generations and their explosive deaths, the universe would consist only of hydrogen, helium, and a trace of lithium. There would be no rocks, no water, no planets with solid surfaces. There would be no chemistry complex enough to form molecules like DNA. The iron that carries oxygen in your red blood cells was once the core of a dying star. The calcium that strengthens your bones was forged in a stellar explosion that occurred long before our solar system even existed. The oxygen you inhale with every breath was created in a star that shone brightly in our galaxy's distant past. We are not simply inhabitants of the cosmos looking out at it from a detached vantage point. We are literally assembled from its recycled remains. Our bodies are temporary gatherings of atoms that have journeyed across the galaxy for billions of years, part of an ancient cycle of stellar life, death, and rebirth. This is perhaps the most intimate connection possible, a direct material lineage that binds our existence to the first flickers of light in the cosmic dark. The universe's grand story of assembly, however, is not a permanent state. Having traced the journey from quantum whisper to galactic city, we must now confront the ultimate destiny of all this magnificent structure. The cosmos is not static. It is an unfolding narrative with a final chapter written by the very forces that shaped its beginning. We live in a pivotal era, a moment where the long age of gravitational growth is giving way to a new, more expansive fate. The key player in this final act is dark energy, that mysterious pressure woven into the fabric of space itself. Its effect is subtle but relentless, acting as a kind of cosmic anti-gravity, causing the expansion of the universe to accelerate. For billions of years, gravity's patient pull held sway, gathering matter into the great cosmic web. But now, on the largest scales, dark energy is taking command. This shift changes everything about the long-term future. As the acceleration continues, the space between galaxy clusters will stretch at an ever-increasing rate. Imagine two islands in an ocean that is not just growing wider, but where the water itself is flowing outward, carrying them apart at a speed that eventually outpaces any possible signal between them. Over timescales of hundreds of billions of years, this is exactly what will happen. Each massive cluster of galaxies, like our own local group which contains the Milky Way and Andromeda, will become an isolated island universe. The space between these islands will stretch so rapidly that light from one cluster can never reach another. The grand cosmic web, the vast network of filaments and walls, will be torn apart. From the perspective of any future observer within one of these isolated clusters, the rest of the universe will have simply faded from view, vanishing beyond an unreachable horizon. The large-scale architecture born from ancient quantum seeds will dissolve into darkness. Within these isolated islands, a slower, colder end awaits. The era of star formation, which has illuminated the cosmos for over 13 billion years, is finite. It relies on a continuous supply of cool gas that can collapse into new stellar nurseries. But that gas is being steadily locked away. Some of it is consumed in the formation of stars, and a great deal is blown out of galaxies by supernova explosions and the fierce activity of supermassive black holes, becoming too hot and diffused to ever collapse again. Furthermore, as galaxies merge and evolve, the remaining gas is either used up or settles into long-lived, low-mass stars. The stellar birth rate across the universe has already peaked and is in a long, slow decline. Billions of years from now, the last star will form. After that, the lights will begin to go out one by one. Stars like our Sun, after shining steadily for billions of years, will exhaust their nuclear fuel. They will swell into red giants, potentially engulfing their inner planets, before shedding their outer layers and shrinking down to cooling embers known as white dwarfs. More massive stars will end their lives in supernova, leaving behind ultra-dense neutron stars or black holes. Planets that once orbited in temperate zones will see their parent stars dim and die, leaving these worlds in permanent deep freeze. Any complex chemistry on their surfaces, any legacy of biology, will be silenced by the cold. The universe, having grown from a smooth, hot beginning into a rich tapestry of structure, will then enter an inconceivably long autumn. The remaining stars will burn out. Black holes will slowly evaporate over unimaginable eons through a process predicted by Stephen Hawking. What remains will be a dilute sea of fundamental particles and radiation, stretched across a vast and ever-expanding emptiness. This is the poignant symmetry of the cosmic story. It began in a brilliant, uniform flash of energy. It will likely end in a dark, uniform sea of stillness. The intricate structures, the galaxies, stars, and planets that were the universe's magnificent middle chapter are temporary, yet their existence is the entire point of the narrative. For a fleeting moment on the scale of cosmic time, the universe woke up. It transformed its latent potential into complex forms, and in at least one quiet corner, it became aware of itself. The fact that we are here to trace this story from its first whisper to its distant, quiet end is perhaps the most remarkable part of the entire epic. This profound connection is not just intellectual, it is woven into the very fabric of our existence. When you look up at the night sky, you are not an outsider gazing at a distant spectacle. You are the universe in a very real sense looking back at itself. The calcium in your bones, the iron in your blood, the oxygen in your lungs, these are not earthly inventions. They are stardust forged in the hearts of ancient suns and scattered across the galaxy by titanic explosions that occurred long before our planet was born. The carbon that forms the backbone of every molecule in your body was created in the fiery crucible of a dying star. We are not simply living on a planet. We are walking archives of cosmic history, temporary gatherings of atoms that have been on an epic journey across space and time for over 13.8 billion years. This transforms our sense of place. We are not insignificant specks on a random rock. We are a localized expression of the universe's own capacity for complexity and self-awareness. The same gravitational physics that orchestrated the majestic dance of galaxies also guides the blood flowing through your veins. The same nuclear forces that light the stars power the subtle chemistry of every thought in your mind. This realization bridges an impossible gap. It tells us that the quest to understand the cosmos is, in a deep and meaningful way, a quest to understand ourselves. By tracing the lineage of a galaxy or the birth of a solar system, we are reading our own extended origin story. This knowledge fulfills a fundamental human longing, a drive to find context and meaning within the vastness. It answers the ancient question of where we come from, not with mythology, but with a narrative written in light, gravity, and the patient unfolding of physical law. That narrative reveals our role not as passive spectators, but as active participants. A universe that can become aware of itself is a universe that has reached a new stage in its evolution. In our curiosity, in our science, in our art, and in our shared contemplation of the stars, we are the universe becoming conscious. We are the means by which the cosmos can reflect upon its own beauty, its own history, and its own profound mysteries. This perspective does not diminish our human experience. It ennobles it. Every act of wonder, every moment of discovery, every connection we forge with each other under this shared sky is part of the continuing story that began with a quantum whisper in the dark. Our place is here now as the part of the cosmos that can listen to its echoes and begin to tell its tale. The entire cosmic story is a single, unbroken chain of cause and effect. It begins with the most ephemeral of events, quantum fluctuations in the first fraction of a second, and ends with you listening to this story. These microscopic ripples were inflated to cosmic proportions, becoming the permanent blueprint for all structure. That faint pattern of density, a whisper of more and less, became the universe's only instruction manual. Gravity, the patient and relentless sculptor, read those instructions over billions of years. Guided by the invisible scaffolding of dark matter, it gathered the primordial gas into the vast filaments and clusters of the cosmic web. At the intersections of this web, galaxies were born. Within those galaxies, the cycle continued. Giant clouds of molecular gas, enriched by the ashes of earlier stars, collapsed under their own weight. Each collapsing fragment spun into a disk, a stellar nursery where a new star ignited at the center, surrounded by a swirling platter of leftover material. In that disk, the final, local act of construction took place. Microscopic dust grains, each a piece of stardust from a long-dead sun, began to stick together. Through collisions and gentle mergers, they grew from specks to pebbles, from pebbles to boulders, and from boulders into mountain-sized planetesimals. These became the building blocks. Gravity again took the lead, pulling these blocks together in a chaotic dance of accretion and impact. They merged into planetary embryos, then protoplanets, and finally, through sometimes violent collisions, into the mature worlds of a solar system. Every single step in this immense sequence was contingent on the one before it. The specific spectrum of those initial fluctuations determined where galaxies would form. The properties of dark matter dictated the timing. The life and death of the first stars set the chemical table. The location of the frost line in our disk decided which worlds would be rocky and which would become giants. The chaotic ballet of planet formation, including a fateful giant impact, gave Earth its moon and stabilized its climate. This is not a series of disconnected events. It is a single narrative, a cascade of causality spanning nearly 14 billion years. Our existence on a stable, life-bearing planet is not a random accident in a chaotic universe. It is the direct, though incredibly intricate, consequence of physics operating from the universal to the infinitesimally local. We are the outcome of a grand chain of events that links the quantum birth of spacetime to the ground beneath our feet. This interconnectedness is our true cosmic heritage, a reminder that we are woven into the fabric of the universe at every scale. The entire cosmic story is a single, unbroken chain of cause and effect. It begins with the most ephemeral of events, quantum fluctuations in the first fraction of a second, and ends with you listening to this story. These microscopic ripples were inflated to cosmic proportions, becoming the permanent blueprint for all structure. That faint pattern of density, a whisper of more and less, became the universe's only instruction manual. Gravity, the patient and relentless sculptor, read those instructions over billions of years. Guided by the invisible scaffolding of dark matter, it gathered the primordial gas into the vast filaments and clusters of the cosmic web. At the intersections of this web, galaxies were born. Within those galaxies, the cycle continued. Giant clouds of molecular gas, enriched by the ashes of earlier stars, collapsed under their own weight. Each collapsing fragment spun into a disk, a stellar nursery where a new star ignited at the center, surrounded by a swirling platter of leftover material. In that disk, the final, local act of construction took place. Microscopic dust grains, each a piece of stardust from a long-dead sun, began to stick together. Through collisions and gentle mergers, they grew from specks to pebbles, from pebbles to boulders, and from boulders into mountain-sized planetesimals. These became the building blocks. Gravity again took the lead, pulling these blocks together in a chaotic dance of accretion and impact. They merged into planetary embryos, then protoplanets, and finally, through sometimes violent collisions, into the mature worlds of a solar system. Every single step in this immense sequence was contingent on the one before it. The specific spectrum of those initial fluctuations determined where galaxies would form. The properties of dark matter dictated the timing. The life and death of the first stars set the chemical table. the location of the frost line in our disk decided which worlds would be rocky and which would become giants. The chaotic ballet of planet formation, including a fateful giant impact, gave Earth its moon and stabilized its climate. This is not a series of disconnected events. It is a single narrative, a cascade of causality spanning nearly 14 billion years. Our existence on a stable, life-bearing planet is not a random accident in a chaotic universe. It is the direct, though incredibly intricate, consequence of physics operating from the universal to the infinitesimally local. We are the outcome of a grand chain of events that links the quantum birth of spacetime to the ground beneath our feet. This interconnectedness is our true cosmic heritage, a reminder that we are woven into the fabric of the universe at every scale. From that quantum foam of the universe's first instant to the spiral arm of a galaxy where a pale blue dot orbits a stable star, we have traced an unbroken line of cause and effect. The story of how early universe fluctuations became galaxies and solar systems is the ultimate creation myth, but it is grounded not in legend. It is written in the rigorous, testable language of physics. This narrative teaches us something profound about our place in the cosmos. We are not separate from the universe we observe. We are deeply, materially connected to the deepest history of everything. The atoms in your body are the legacy of ancient stars. The stability of your world is a gift from a chaotic, formative past. The very fact that you can ponder these ideas is a testament to a cosmos that evolved the capacity for awareness. As you look up at the night sky, remember you are not just seeing points of light. You are seeing the present-day result of those ancient quantum whispers, stretched and sculpted over eons into a tapestry of structure. You are witnessing the ongoing story of which you are a part. If you found this journey through cosmic history enlightening, please subscribe for more deep dives into the universe's greatest mysteries. We would love to hear your thoughts on this profound connection in the comments below. What part of this cosmic story resonates most deeply